All right, the last section we are going to look at this week is 7.5. We're going to split this up into 2 days. So we'll do half today and then half tomorrow. So what I want to look at is what happens when we have something added or subtracted inside the argument. Something plus something or something minus something. And I want to look at how we can simplify that. Because we don't want to ever really have a plus sign inside an argument. It's going to make things very complicated. It's okay to just have an x for the argument, that's fine. But we really don't want to have plus or minus something. Now, let's just think about it in terms of transformations first. When you do a plus 3 on the inside, what would that do to your graph? Yep.
It would shift it horizontally.
Yep, 3 units to the left. So this would translate it 3 units to the left. And then what about when you add a number on the end? What kind of transformation is that?
Horizontal stretch.
Vertical stretch.
What is it?
Vertical shift.
It's a vertical shift. So just from the perspective of transformations, are those the same transformation? No. One is a horizontal shift, one is a vertical shift. So the point is, you can't say that that equals that. That doesn't work. All right, you can't just like take the word sine and pretend like you're going to distribute it. That doesn't work at all. So then I want to know what does work. Right? If I have addition or subtraction inside the parentheses, what can I reduce it to so I don't have that? So we're going to look at 4 different formulas. Maybe 6, I'm not sure. But we're going to do 2 for sine, 2 for cosine. We're going to do sine with a plus, then we'll do sine with a minus. We're going to do cosine with a plus, and then we're going to do cosine with a minus. So I'll show you what the formulas are. And we're going to start out with what's called the cosine difference formula. Okay. Cosine difference formula means the function is a cosine and you have subtraction inside. Okay, we don't, it's not hard to prove some of these formulas. And we might do one where we prove it. This one's a little time consuming to prove, so we're just going to kind of start with this, use this as kind of our point where we build everything off of, and things will be a lot easier. If you want to really prove that, you can, but it would probably take about 10 or 15 minutes. It would take a good amount of time. So what's happening here? Inside the first part on the left, you have 2 different numbers that are being subtracted. If you don't want to have this minus inside here, you can rewrite it. And the way you would rewrite it is cosine alpha, cosine beta, plus sine alpha, sine beta. When I read that, I'm going to call this one the first, and I'll call that one the second. So it's cosine first, cosine second, plus sine first, sine second. A couple things to notice. Originally, you had a minus. When you rewrite it, it turned into a plus. With the cosine formula, whatever symbol is here, you always have the opposite one here. So if it's a plus inside, you'd have a minus over there. If it's a minus inside, you have a plus over there. So that's our first formula. Yeah.
Is it kind of just the equivalent of boiling it out?
You mean to prove it? Like if you were going to prove why that's true?
Yeah. Or just
It's a little bit more complicated. Yeah. Yeah, it's a little more complicated because you're not really raising anything to a power here, and that's generally where you FOIL when you raise something to a power. There's no powers in this one. So, all right. So what can we do with that formula? Well, we can figure this out. remember when we did unit circle, we had 12 different points that we worked with in the quadrants. We had the 30, the 45, and the 60 in every quadrant. But there were gaps. Okay? If you put the 30, the 45, and the 60 on the circle, you kind of have a little bit of an extra gap here and a little bit of a gap there. And you have those gaps in each quadrant. Well, those blue points that I just put on there, those are all the multiples of 15. So what we're going to be able to do is, using that identity somehow, we're going to be able to figure out the multiples of 15 now on the unit circle. Okay, a couple things we need to remember. Because we're going to be tying it in with the unit circle, we need to remember a couple of these as decimals. Remember, root 2 over 2 is approximately 707, and root 3 over 2 is about 0.866. If we can remember those two from the unit circle, that's going to save us from having to go back and relearn everything we already know about the unit circle. Okay, so these are two numbers that came up a lot. The root 2 over 2, that came up in what kind of triangle? The 30-60 or the 45-45? Which one? Yeah, that came up in the 45-90. And the root 3 over 2, that one comes up in the 30-60-90. Yep. And we proved where these numbers came from. They come from Pythagorean theorem. And we did that back at the beginning of chapter 6. So now, let's see if we can figure out the cosine of 15. Now, it says that it wants what kind of answer?
An exact answer.
Right, an exact answer. So doing this is not an exact answer. Okay, we don't want a decimal. So what we need to do is think about how you can write the number 15 as a difference. Okay, we're going to somehow use this formula. Now, there's a lot of ways to write 15 as a difference. 16 minus 1, 17 minus 2, lots of different ways. But you're very restricted with the numbers you can use in those two spots. The numbers in those spots have to be multiples of 30 and 45. That's all you can use. Right, we could do 45 minus 30. So now in that problem, alpha is 45 and the beta is 30. So let's rewrite that using the formula right there, except instead of alpha and beta, fill in the two numbers, 45 and 30. Once we do that, we'll have something we can simplify. So it's cosine of the first angle times cosine of the second angle plus sine of the first angle times sine of the second angle. Now, what we have there is 4 different things we need to figure out. Right? Every one of those we've already done on the unit circle, because they're all multiples of 30 or 45, and they're all sines and cosines. Now, because they're sines and cosines, these are the only two numbers that will ever pop up that are not nice numbers. Okay? So if you don't remember how to find the cosine of 45, you can type it in on the calculator, and it'll give you the decimal, but we need it as an exact answer. So what is the cosine of 45?
Square root of 2 over 2.
It's the square root of 2 over 2. And that would come from drawing your, if you were going to do the whole thing out, You draw your triangle. You label each side as root 2 over 2. And then you'd have to remember that cosine is the x value. And the x value, in this case, is root 2 over 2. Okay. Cosine of 30. If we were going to do the cosine of 30, and you were going to do it on the unit circle, you put 30, draw your triangle, and in the 30, 60, 90, you have a long side and you have a short side. Does anybody remember the length of the short side in the 30, 60, 90?
Isn't that the bottom right
That's
there?
the long side.
Oh,
The hypotenuse is 1. And what was the short side?
okay. I know. I'm trying to find it.
This is with the unit circle.
I know. She can probably find it faster than I can. Oh, wait.
So pi over 4, that would be like a 45-degree angle. But we're looking for the length of a side. 1/2, yes. And now, to find the cosine, once you know the coordinate, the cosine is which part of the coordinate?
The
Uh,
the x as well.
It's the x.
Yes.
Yeah.
Square root 3 over 2.
So it would be square root 3 over 2. So that's the process you'd have to go through if you didn't know when you do cosine 30 that 0.866 is the square root of 3 over 2. Okay, so using the calculator, I can get the decimal, and I recognize that as root 3 over 2. Okay, but if you can't memorize that that's root 3 over 2, you're going to have to do that every time. It's really going to slow things down. All right. Now let's just try to remember the 45s. So 45 is right there. That's an isosceles triangle. How long was each leg in the 45, 45, 90? They were both square root of 2 over 2. And the first one they want to know is the sine. What is the sine? What part of the coordinate was that? It was the y. And if you write the coordinate here, what is the y value? It's square root 2 over 2. Yep. Or if you type in sine 45 and you recognize 0.707 as root 2 over 2, that saves us a lot of time. And now the sine of 30, well, we already got the coordinate right there. What's the what letter is the sine again? It's the y, and the y is 1/2. So the sine of 30 is 1/2. Or if you just type it in, that's an easy one to recognize, 0.5, 1/2. Okay. Now let's just simplify that and put it all together. When we're multiplying, we can go straight across. What's the square root of 2 times the square root of 3? Square root of 6. Over my denominator will be 4. And the square root of 2 times 1? Square root of 2. Over 4. What's the common denominator? 4. So put it all together with a common denominator of 4. that should be the cosine of 15. Let's check. So that's the cosine of 15 if you type it in as a decimal. Now let's try square root 6 plus square root 2 divided by 4. Yep. That's the exact answer. Whether you're working with any multiple of 15, it always kind of comes out to something like that. Root 6 plus root 2 over 4, root 6 minus root 2, negative root 6 minus root 2. But it all has like a root 6 and a root 2 and a 4 in the bottom. Okay. Any questions on that one? Let's try one a little different. Let's try this one. So this is a verify, okay, kind of like we did yesterday. They want you to verify that that is exactly the same as that. Now, this is going to use something we learned today. With Pythagorean and all that stuff that we learned yesterday. That's still good, it's just that's not going to help you in this problem. This left-hand side follows the pattern of what formula I just gave you. Cosine difference. That left-hand side is a cosine difference. Cosine difference. So fill that in to your formula and see what happens. That's going to be your alpha. That's the first angle. And the second thing you're going to plug in is theta. So I'm not using, I could have used beta. I could use any letter I want here, but I used theta. Okay, so remember the pattern. It's the two cosines on the left and the two sines on the right. And the angles are in order. 1, 2, 1, 2. Okay. All right, so two cosines on the left. Two sines on the right. Fill the angles in. 1, 2, 1, 2. So 1, 2, 1, 2. And forgot my sign. And what goes between the two parts? It's always the opposite of what you have right there. At least when you're dealing with cosine. All right. So now, some of that we can simplify, some of it we can't. Out of the two factors on the left, which one can we simplify? Right, because that's a number, right? Cosine theta, well, can't do anything with that. But cosine of pi over 2. Think about pi over 2. What's pi over 2? 90. Where's 90 on the circle?
Straight the top.
0, 1.
Top. And what's the coordinate at the top? 0, 1. And cosine is which letter? Cosine is the x. So cosine of 90 is 0. Okay, let's do the next one. Sine of pi over 2. Okay, same coordinate, but sine is which letter? It's the y. What's the y value?
1.
So it's 1 times sine of theta. This whole part turns into a 1. This part turns into a 0. What's 0 times cosine?
0.
So this is gone. What's 1 times sine? And that's what we were supposed to get. So that's, today, that's how the verifies with identities are pretty much going to work. They're much easier than yesterday. Any question on what we did there? I have some, bless you, I have something just like that on the test. What I might do is say, you know, if you were trying to prove this exact problem, I might say, what would the second step of the proof be? And you'd have to write this down. You'd have to tell me that it turns into a 0 and that turns into a 1. So you'd have to know that. Right, let's try another one. Okay, another verify. What pattern does that left-hand side fit? That's the cosine difference. Okay, there's 4 patterns you're going to look at. Cosine difference, cosine sum, sine difference, sine sum. Okay, that's cosine difference. Okay, it's pretty easy to tell which one it is. Just look at that and then look at that. Okay, it's cosine difference. That's where you have the 2 cosines together on the left, the 2 sines together on the right, and what goes between them?
Additions.
Addition. It's easy to remember that when that's the only one we know right now. Once we learn all 4 of them, they're all kind of similar, so it's hard to remember which one is which. But that's the cosine difference. And then you fill in your angles, 1, 2, 1, 2. So pi, theta, pi, theta. Okay. Pi. Let's think about that on the unit circle. Where's pi? 180 degrees. So where is that?
On the left and the right side.
On the left, which is negative 1, 0. And cosine is which letter? X. And in this case, x is? So negative 1 times cosine. Plus, now they want the sine of pi. Sine is which letter? The y. What's the y in that coordinate? 0. That's usually what happens in these kind of problems. One part comes out to 0, and it cancels. And what's negative 1 times cosine? And that's exactly what we were supposed to get. Okay. So given the choice of having to work with either what was on the left or what was on the right, I'll just point. The right side is a lot simpler because it doesn't have this complicated thing inside the parentheses. It doesn't have any subtraction. I would rather have a minus in front. That's a lot easier. It's just like having a negative 1. Right? That's more complicated. So we were able to simplify it. Question on that one? Okay, so that's the cosine difference. Let's look at the cosine sum. Well, if I just go back to it, I think you can probably figure out what it is.
You just have a minus instead of plus.
Okay, yeah, we're just going to change that to a minus. That's all that changes. It's the only difference. The cosines are still grouped on the left. The sines are grouped on the right. We just have a minus instead of a plus. Right there. Okay. So that's the cosine sum formula. So cosines on the left, sines on the right. 1, 2, 1, 2 for the angles. So first, second, first, second. And when you're dealing with cosine, it's always the opposite of what you have right there. Not with sine, okay, but with cosine it is. Okay, so that's the cosine sum formula. Now, technically, anything you can do as a sum, you can do as a difference. So you really don't need the sum and the difference formula. It's kind of like if you said to me to do 5 minus 2, and I didn't know how to do subtraction. Well, instead of doing 5 minus 2, I could just think of it as addition and say 5 plus negative 2. So any subtraction problem can really be done as addition. So it just makes a few things more convenient, so you don't have to think of it that way. But again, it's not necessary to know that formula. Okay, let's try the cosine of 75. Exact answer. So to figure out an angle that's a multiple of 15, the goal is to split it up into 30s and 45s, or multiples, like you could use 30, 60, 90, 120, any of those numbers. And you can do a difference, or you can do a sum. You can do it any way you want. Whatever way comes more natural to you. So how can I split up 75?
50 and 25.
What is it?
50 and 25.
Okay, now are 50 and 25 multiples of 30 and 45?
30 and 40.
Yeah, because if we don't do multiples of 30 and 45, we're not going to be able to do the unit circle. Okay, because all we know are 30s and 45s. Okay? So yeah, I would do 30 and 45. All right. So let's split it up. Can anybody tell me how to break all of that up using the cosine sum formula?
30 degrees would be 1 and 45 degrees would be.
Okay, so those are going to be my two angles, my 1, 2 for my angles. And what's going to be the whole thing? Yep.
Cosine 30 times cosine 45 minus sine 30 is sine.
Yeah. Now, we've already done all of those trig functions. Okay, if it's very similar to the one we just did. So we can hopefully go through a little quicker. Cosine of 30 is how much? Root 3 over 2. How about cosine 45?
Root 2 over 2.
That's going to be 0.707, root 2 over 2. Sine of 30? Half. And the sine of 45? Think of the coordinate for 45 degrees and then think of the y value of it.
Root 2 over 2.
Root 2 over 2. Okay, so let's put it all together. It's already going to have a common denominator. That's going to be automatic. What's the common denominator?
2.
4, right? Because we're going to multiply those together. So I told you, you always end up with a 4 in the bottom and then like a root 6 and a root 2 kind of thing in the top. Okay. We're going to have subtraction. What's root 3 times root 2?
Root 6.
6. And 1 times root 2?
Root 2.
There you go. Okay, I'm not going to check it, but that is right. So if you want to check it, type cosine 75 in, and then type that in on your calculator. Now, what if, let's say that we didn't want to do it as a sum. You didn't remember the sum formula. I don't know why you not remember that and remember the difference, but let's just say for some reason you only remember the difference. Does anybody see how you can get 75 as a difference instead of a sum? And remember, the numbers you can use, numbers like this. And there's some overlap between multiples of 45.
135 and 60.
Yeah, you could do 135 and 60, and you would get exactly the same answer. Yep. But now, instead of doing it with the sum formula, you would go back to the difference formula. So anything you can do as a sum, you can do as a difference, and vice versa. Any question on that one? Okay. So up until now, a couple things have happened. The cosines have always been grouped on the left. The sines have always been grouped on the right. And this has always been the opposite of that. Okay. That's going to change a little bit with the sine sum formula. It looks kind of similar, but it's a little bit different. What do you notice is different?
The signs are opposite.
Okay, yeah, the plus minus, you have to be careful when we say SIN or SIGN, what we mean by sign. This sign
Yes.
is the same.
And then there's one sine and one cosine on each side.
Right, they're not grouped on the same side anymore, they're mixed. So it's sine, cosine, cosine, sine. I write it like that So I can always say 1, 2, 1, 2. That's the reason I put it in that order. So I can always write my angles down. First, second, first, second. That's how I like to do it. So that's the sine sum formula. Trig functions are mixed, and the plus sign matches the plus sign. What do you think would change in the sign difference formula?
This division with this would be, the addition would match the subtraction.
Right. It's still going to be mixed. Cosine, sine, cosine, cosine, sine. But we'll have minus matching a minus. That's the only difference. Angles are still first, second, first, second. So now this enables you to do all the things you could do with the cosine formula. You could do the sine of 15, you could do the sine of 75, all kinds of stuff. I think I picked one we'll do in a second. Let me just see. Everyone have the sine sum and difference? So now let's try the sine of I gotta pick one that's a multiple. 15, so let's do 195. You can break that up as a sum, you can break it up as a difference, however you want. You just have to make sure you use 30s and 45s. Okay, so anybody see, again, sometimes it helps if you're not sure, write down the different numbers you can use. That's some of the multiples of 30. Some of the multiples of 45, it's not all of them. I'm not going to need anything higher.
150 plus 45.
Okay, you could do a 150 plus a 45. I was also thinking a 60 plus 135 as a sum. So either of those ways work for a sum. How about as a difference? Yep, you could do 225 minus 30. So there's lots of, that's what I'm saying, lots of different ways you can do it. I'll do it the first way that somebody said, was it 150 and 45?
Mm-hmm.
And if you're wondering, what happens if I don't pick multiples of 150 and what if I don't pick multiples of 30 and 45? Then you're not going to get the 0.707 and the 0.866 number. You're going to get numbers you don't know how to write with square roots. So you've got to pick 30s and 45s. Okay. So first of all, when we break up the sign, are the trig functions grouped or mixed? They're mixed. Sine, cosine, cosine, sine. Sine, cosine, cosine, sine. What's going to go between the two parts?
Sine.
Right? The plus sign matches. And then fill in your angles. 150, 45, 150, 45. All right. And if you don't know them off the top of your head, hopefully when you see the decimal, it'll jog your memory. Sine of 150,
1/2.
that's the 1/2. Yeah. Cosine of 45, we've done that one a lot today. That's your root 2 over 2. Okay, cosine of 150. That's that one. Yeah, it's just a negative in front of it. It's still negative root 3 over 2. So that's actually going to be subtraction. And then the sine of 45?
Root 2 over 2.
Same as the cosine of 45. Okay, so common denominator? 4. And again, because you're adding a negative number, you might as well just make it subtraction in the top. And what's going to be on the left part? Square root 2. And the right part? Square root of x. Okay, I'll check that one just so you can see that I'm actually telling you the truth. So that's the sine of 195. And now if you do the square root of 2 minus square root of 6 I messed up, I hit something. And then divide that by 4, you get, it's a rough day. Let me type it in again. Square root of 2, get out of there, minus the square root of 6, close that, there we go. You get the same thing. It's a lot of parentheses to type in. Any question on that one? All right, now, let's say I asked you to do something like the tangent of 15. There is a formula for tangent. I'm not going to show you what it is. Okay, it's a little more complicated. What did we learn about tangent yesterday? What's another way you can write tangent?
Sine over cosine.
Sine over cosine. So what would the tangent of 15 be the same as?
Sine of 15 over cosine.
Right. Do we know how to write 15 as a sum or a difference? Yeah. Do we have sum and difference formulas for sine and cosine? Yeah. So if you had to do a tangent problem, this isn't the fastest way to do it, but you could change tangent to sine over cosine, and essentially now you have 2 problems to do. You do the sine of 15, get that answer, get the cosine of 15, and then take the 2 answers and divide them. So you could figure out a tangent by doing it this way. Right? I'm not going to go through that in detail, but that's how I would think of the tangent rather than learning the formula. It's not a bad formula. It's just one more formula you'd have to remember. So that's how we're going to think about tangent. But the most important ones are sine and cosine. Right? That's what I would really focus on knowing how to do. Okay. Let's look at that. I want to think of that just in terms of transformations. When you put a 2 inside the argument, what kind of transformation is that? Specifically in this one, it would be a horizontal compression by a factor of 2. Yeah, this would squish it horizontally. What would this 2 do? That would stretch it vertically. Is stretching vertically always the same as compressing horizontally? No. Maybe you could find some weird example where it works out, but no, these aren't the same. So that leads us to another formula. What happens when you have a 2, specifically just a 2? If it's a 3 or a 4, it starts to get harder. But if it's a 2 in front of x, how do we deal with that 2? Right? Well, let's look at this. You guys should know a way, if you use what I've shown you, to get rid of that 2 in front of the x. And you can't just put it in front. That doesn't work. It's not the same thing. Think about what's that? X plus x, yeah. Think of, instead of 2x, think of a different way that you can write 2x. X plus x. Now that is something we just learned. What is this? It's the sine sum formula. So apply the sine sum formula to that, and you'll know what that is. Let's see what it is. Sine sum. Do we group the trig functions, or are they mixed? Mixed. Okay. What's going to go between them? Plus or minus? Yep, it's plus. So remember, with that, we always match it up. And what's going to go, well, what is my first thing that I'm using in the sum formula? An x. What's my second thing?
X.
They're both x. First, second, first, second. So I have a sine times a cosine plus another sine times a cosine. It's kind of like having xy plus yx. Or you can think of it as xy plus xy. So what's sine times cosine? Plus cosine times sine. So it's nothing to really look up.
Equal 1.
It's nothing to really look up. It's just more like, well, what would this be algebraically? What's xy plus xy? 2xy. So what's sine cosine plus cosine sine?
2 sine cosine.
Yep. That is how you get rid of having a 2 inside the parentheses. 2 sine 2x turns into 2 sine cosine. Let's try it with a number. Somebody pick a number for x. 30. So if I take the sine of, if I fill in 30, 30 times 2 is 60. Okay, that's the sine of 60. Now, let's do 2 sine, you said 30, right? 2 sine 30, cosine 30. I'm typing it in the way it's in that box. It's exactly the same thing. So this shows you how to get rid of a 2 inside there. And what do we call this thing that's inside here? It's the argument. And specifically with a trig function, the argument represents an angle. Yes. So this represents an angle. 2 represents doubling. That's why this is called a double angle identity. Double angle identities show you how to get rid of a 2 when it is in front of the argument. Okay. And there's a double angle formula for sine, there's one for cosine, and there's one for tan. The sine one is the nicest looking one. And that's also pretty much the only way you would ever see the double angle formula for sine written. When you write the double angle formula for cosine, there are a couple different ways you can write it. That's one way. Looks kind of like something we studied, sine squared plus cosine squared, but it's not. It's cosine squared minus sine squared. That's total, so that's different. Could also write it that way. Or you could also write it that way. They're all equivalent. Which one you use? Well, it depends on the problem. If I was doing a problem and for some reason I did not want to have any cosines in it, well, then I would use the second one. If I was doing a problem and I did not want sine in it for some reason, I would use the last one. And that's the double angle formula for tangent. I'm going to give you the tangent one. I don't think we're going to focus too much on that. We're going to focus more on the sine and cosine. So I wouldn't be as concerned about the tangent. Everybody have the double angle formulas. Actually, we almost finished the whole section. So tomorrow we can spend a lot of time on the homework and then review some questions. Yeah, that's the last question, actually. All right, so let's see if we can write that just with sines and cosines. No 2's inside. 2's outside is okay. No 2's inside. Is there any part of what they gave us that's already okay? Yeah, we don't need to do anything with this. It's already the way they want it. It has cosine just x. How about the second part? Is that the way that they asked us to write it? No. What's there that we don't want there? The 2. So how can we rewrite this so there is no 2 inside the parentheses?
2 sine x cosine x.
Yep. Now at that point, you've technically done what they wanted. They said rewrite it using just sines and cosines, and that's exactly what you have. You just have x's for all the arguments now. But they might ask you to simplify that. And what do both of those have in common? Oh yeah, I didn't
A 2
see
and a
that.
cosine.
They both have a 2 and a cosine. So you can factor that out. If you factor that out from here, what's left?
There's nothing
1
left
plus
on
sine.
sine.
Yeah, 1. Because if you distribute it, you got to make sure that you would get back what you had. And what would you have to put here?
1 plus sine plus 1. For 1 plus sine plus times cosine. Or no, it would be a negative
Plus
cosine.
1 plus sine x.
Just 1 plus sine x, right? Because if you distribute this back out, 2 cosine x times 1 is 2 cosine x, and 2 cosine x times sine is 2 cosine x times sine. So if they asked you to factor it, that's what they'd be looking for. That's it. Okay. Any question on that? All right. So tomorrow we will go through a few more examples of that. But that's pretty much all of 7.5. Okay, so homework tonight on page 417. On question 31, there's multiple parts to it. You just have to do part A. So we'll go over that tomorrow. We'll review a little bit more of 7.5, and then first test, well, last test for progress reports will be on Friday. Yes.